Hello everybody, thank you for joining me once again. We're looking now at question number 7 on the 2006 grade 12 Euclid contest. So, we've got a part, we just need the final answer. The sequence 2, 5, 10, 50, 500, I don't recognize this sequence, is formed so that each term after the second is the product of the two previous terms. 2 times 5 is 10, 5 times 10 is 50, 50 times 10 is 500. Okay, alright, it makes sense now. The 15th term ends with exactly k zeros. What is the value of k? Alright, so just looking at it naively, looks like we get 2 with no zeros, 2 with 1 zero, 2 with 2 zeros, maybe. I don't know, there's not a whole lot to go off of here. So let's explore by writing down a bit more of the sequence. We understand how it's made. It's not particularly difficult to calculate. So let's see where we can go with this. 5 times 5 is 25 followed by 3 zeros. 5 times 25 is 125 followed by 5 zeros. 125 times 25 is 3125 followed by 1, 2, 3, 8 zeros. Alright, so the numbers are getting bigger, but what have we got here? No zeros, no zeros. 1, 1, 2, 3, 5, 8. And this part should be familiar to you if you've done any math contests or really any recreational math. This is the Fibonacci sequence. Okay, now, is it actually the Fibonacci sequence, or they're just throwing me off because they don't expect me to calculate more than this? Because I'll do it, I swear I'll do it, alright, so what can we do? We keep adding the number of zeros each time from the previous two, but how do we know another zero won't creep in? Like, we had no zeros here, and then suddenly, bam, a zero. And I think that's because we had a 2. These look like powers of 5 followed by zeros. So that should always hold, right? And what's the best way to write that? So I'm going to write these with prime factorizations. It's 2 to the 1, 5 to the 1, 2 to the 1, 5 to the 1, 2 to the 1, 5 to the 2, 2 to the 2, 5 to the 3. Now I'm adding them up each time. So 1 plus 2 is 2 to the 3, and then 2 plus 3 is 5 to the 5. And if I get out my calculator, I'll check, yeah, that actually works out. So, what can we do here? Number of zeros equals number of factors of 10. The powers of 2 are always less, so we need to make a 10. We need a 2 and a 5. So the number of powers of 2 is less than the number of powers of 5. So it's the powers of 2 that are going to limit us. So number of zeros equals power of 2, or the exponent of 2 here. Once we're beyond the second term. Obviously this fails for the first bit. 2 has no zeros. Okay. And now it looks like the powers of 2 are all the exponents here are growing by Fibonacci numbers. So I think the easiest thing to do is just write out, let's say, So we'll have first term, second term, third term, fourth, fifth, sixth, seventh, eighth, ninth, 10th, 11th, 12th, 13th, 14th, and we need 15th. 2 to the k, 5 to the k. So this will be 1, 0, 0, 1, 1, 1. And then it's just the sum of the previous two. So this will be 1, then this will be 2, then this will be 3. I'm going to fill this one out just for the sake of completeness. 8. And hey, we 1, 2, 3, 4, 5, 6, 7, 8 is our power of 5 here. We should get 8 here as well. Yeah, 5. And that gave us 8 zeros, because that's the limiting number. You could also, I guess, have a third row of this chart saying number of zeros, and then you get 0, 0, and so forth. But I think it's clear from here. 13, 13. So it seems like the powers of 5 are just one ahead of the others, or the powers of 2. 21, 34, 34. This is just me doing my Fibonacci numbers from memory. 89 comes next, 144. 144, and then 233, and then I think it's 377 after that. And then I think 660, or, no, 610 apparently. Yeah. But that's all we need. We need 233, so 233 zeros. Alright, not a bad little question. The 233, once you realized Fibonacci, if you were confident that that really was it, you could probably get this 233 very quickly, but I wanted a bit more explanation here. Okay, so that was A part, and now we've got B part, the written one. Suppose that A, B, C are 3 consecutive terms in an arithmetic sequence. So I could rewrite B as A plus D and C as A plus 2D. That's how arithmetic sequences work. Common difference. Prove that a squared minus bc, b squared minus ac, and c squared minus ab are also 3 consecutive terms in an arithmetic sequence. And if we didn't know what it was, because I don't think it's always in the curriculum everywhere, but an arithmetic sequence is a sequence in which each term after the first is obtained from the previous term by adding a constant. For example, 3, 5, 7 is an arithmetic sequence with 3 terms. Okay. Knowing these arithmetic sequences and geometric sequences is a major help in these contests. So I'm going to say let D equal the common difference. So A, B, C is really just A plus D, A plus 2D. So now, A squared minus BC, I think that was the first one, right? I'm just going to change all of these and keep the A and the D's, and then see, I think I should be able to regroup or something to get a common difference. So this is A squared minus A plus D, A plus 2D. So that's going to be A squared minus minus 3AD minus 2D squared. Okay. And those two A squareds will cancel out. We'll deal with that in a moment. This is A plus D squared minus A plus 2D. So that's going to be A squared plus 2AD plus D squared minus A squared minus 2AD. Okay, and I'll simplify things now. That cancels, that cancels, that cancels, that cancels. So we're left with, here we're left with D squared, here we're left with negative 2D squared minus 3AD. And now A plus 2D all squared minus A plus D is A squared plus 4AD plus D squared minus A squared minus AD. So once again, the A squareds are going to cancel. This guy will cancel with one of these. And we'll keep it all in the pinky red. We get D squared plus 3AD. Okay, so am I missing something? This doesn't seem, oh, there it is, there's my mistake. It's not d squared, it's 4d squared. I was going to say, this doesn't seem to be working out, but there it is, 4d squared. Okay, and notice we have a common difference. So the d squared, the middle term, minus negative 2d squared minus 3ad is equal to 3d squared plus 3ad, and that's the difference of the last two as well. Therefore, a squared minus bc, b squared minus ac, and c squared minus ab are an arithmetic sequence. You might add another sentence in there explaining the common, calculating the common difference a little more separately. But, you know, there it is, and I don't think there's a whole lot more to this question, really. So I think that was a pretty short written question, but don't worry, they will get longer. We'll just double check. Was there anything else I had to show? Prove that there are three consecutive... No, we're good. But the written questions will get harder as we're going to get into 8, 9, and 10. And 10 should be particularly challenging, I hope. It's always nice to end the Euclid with a very good challenging question. Separates the men from the boys, the women from the girls. Good challenging question is a nice thing. But we'll get to 10. Up next is going to be question number 8. Thank you guys as always for watching, and I will see you in the next video.